Hi, everyone. So yeah, I'm Donal McBreen. I'm a programmer at 37 Signals. And so today I'm going to talk about our new disk-backed Rails cache that we're calling Solid Cache. So we've been using this on hey.com since about February and since the start of September on Basecamp. Okay, so there's a tagline. So let's look at that. Okay, so if we start caching things on disk instead of memory, which is kind of the standard approach where you'd use something like Redis or memcached, we're definitely going to be able to have bigger cache because disk is so much cheaper and you can get more for your money. As I said, cheaper, it's definitely going to be cheaper, but our question was, well, will it be faster? So the individual operations, we're not expecting those to be faster, but hopefully the cache overall will make our application faster, which is what matters really. So let's see. Right, so this is our Rails cache store quadrant. So we've got local and remote caches, we've got memory and disk caches. So there already is a disk cache, the file store, built into Rails. But there's nothing in this kind of bottom right-hand quadrant built into Rails. So we're kind of targeting that, the remote disk cache. So we had some design criteria kind of before we started, so I'm just going to talk through what those are. So our first design goal was that we would use a database. Okay, so this was kind of because it made so many things so much easier if we just start with a database, right? You've got connection libraries, you've got SQL, so we've got our language for inserting things into the cache, selecting them, deleting them, and so on. You've got indexes, so we can use an index to find the records we want quickly. We don't need to deal directly with the file system. The database is going to do that for us. And we already have a database, so maybe we can put our cache in there. Maybe we don't want to. Maybe we want to put it in another database or shard it between multiple databases. Well, that's fine because Active Record has lots of connection handling stuff built in for us that we can use for that. And the big thing when you use a database is that they come with memory caches built in. We use MySQL, it's got the buffer pool. So actually, most of the time, you're not going to disk. Buffer pool hit rates are like 99% plus. So like you're actually going to disk maybe like 1 in 500 times, really. Okay. And the second part of that was we wanted it to be database agnostic. So we wanted this to work. You could use it with SQLite, you could use it with MySQL, you could use it with Postgres, or whatever database you're bringing. The second thing was that we wanted it to be plug and play. So 3 steps, that was the aim. So install the gem, run the migrations to build your cache table, set your cache store in your config, and you should be good to go. So that was our aim. That it should be as simple as that to install it. And the second part of that was no cron. We don't want you having to set up these separate tasks before you can use the cache, something to like expire data out of it or anything like that. Okay, and our third criteria was that it should be fast. So we're talking about, the overall aim is to make your application faster, but we do want the individual cache operations to be as fast as we can make them. We're not going to get the same speed as you might with Redis or memcached. There you're talking single microsecond operations. With a database, it's more like 100 microseconds. But those are both very small numbers. So let's see how close we can get it. So I'm going to show, here's the schema. This is not the actual schema, but this is kind of the sort of simple starting point you need. This is all you need to build a cache. It's kind of, simple key value store. We've got a key, we've got a value, we've got an index on a key. Great. Now we've got a cache. We can insert stuff, we can query it. All works great. Right. So we couldn't just stop there, though, because we have this problem of cache expiry. So this is kind of the biggest issue that we sort of faced when trying to implement this. This comes built into Redis and memcached. You just set up your server, say, give it 64 gigabytes of RAM or whatever number you want, and it will handle the expiry for you. You just add stuff to the cache, and when it gets too full, it will just start removing stuff for you. But databases, they like data. They don't like to delete it. They're not going to delete things for you without you telling them to. So we're going to have to do this ourselves. And we had these 2 criteria So the first one was the age of items, and the second was the actual size of the cache. So we'll talk through those a little bit. Okay. Why do we want to expire things by age? Well, we've promised our customers that. If you're using Redis, it uses this probabilistic least recently used algorithm, where it basically randomly selects some items and removes the oldest ones. So if you're using Redis for your cache, you could have some really old data in there that's just never been randomly selected. And if you've promised your customers, we've deleted all your data, if you go look in your cache, you might discover that that's not actually the case. So we wanted to build this cache, so you say the day, 2 weeks, that's as long as you want to keep the data, and then we will make sure to delete the data from that point. And how we're going to do this was we'll use an index. That's, it's easy with databases. You can just index on the age of the items, and then you can easily find the oldest items. Okay. This was the harder problem. How are we going to expire things by the size of a cache? So first of all, why does this even matter? We're already expiring things by age. Well, your cache could have variable growth rates. So you might, if you're doing fragment caching, you might have some partial that just gets used on every page, and then you change it, and it changes the digest, and suddenly you get this huge influx of data into your cache. So the rate that your cache is going to grow at will vary over time. So we need a way to see how big is this actually. And what we really want to know is how big is it on disk? How much space are we taking up? And we sort of looked at a few approaches. So one was we could look at the size of the files on disk. So that sounds good, but the chances are if you look at your application, go to one of your applications, you can't get your hands on that information. You could make some changes to get your hands on it, but they're not going to be, one of our criteria is this is database agnostic. It's not going to be something database agnostic. It's not going to be easy to get your hands on it. So that's not that useful. So that was out. Another option is we could look at the database statistics, but you may not have access to them. They're going to be database specific, and they're not going to be real time, and we want real-time information. So then the last thing we looked at was, could we use the row count as a proxy? And I think that should be a fairly good proxy for the size of the cache. But again, there's a problem. It's really slow. On Basecamp, we're looking at hundreds of millions of rows in our cache, and doing a count star on that table is just going to be too slow. So we'll come back to this, but that's one of the problems we're trying to solve. Okay, so I'm going to quickly have a look at some expiry algorithms because we need a way to choose kind of what is the oldest item. So really we're talking about here is when we say we're going to start removing the oldest items, how do we define what the oldest item is? So the kind of simple first expiry algorithm would be FIFO, first in, first out. So to do that, we're going to change our schema, add this created at field, and put an index on it so we can find the oldest records. And let's just have a look at how that looks. So we've got a cache here, we've got the index, we've got our table. Everything's nicely and neatly ordered. Everything's in the same order, which is kind of logically and probably physically how it's going to look on disk, because we're adding things. The data is going down into our table, record by record. It's going to get laid out in blocks in the table, and they're going to be ordered in the order that we add them into the cache. And then our index is going to be ordered by created at. So you have this kind of nice, neat, everything's lining up nicely. Okay, and then let's add something to our cache. So this little yellowy-orange blob wants to join in, and we pop it in there, and an item's going to pop out the end of the cache. And as you add more items, it's going to move down, and the other one's going to disappear out the other end, and eventually our item leaves the cache, and kind of round and round and round we go. So that's a super simple algorithm. But if you look at like Redis or Memcached, that's not what they use. They use, well, in Redis's case, something a bit like least recently used, and Memcached is kind of pretty much least recently used. So this is basically a different way of deciding what your oldest item is. So instead of by created date, we're going to do it by access date. So this is basically the same schema, we've just renamed our column. Okay. So now we've got a cache again, but now we're using least recently used. So what happens? First thing we're going to do is we'll read an item. So we're going to read this one here. Because it's been read, it's been accessed, we're going to update the accessed column, and it's going to move to the front. So it's now the newest item in our index. And our index is what we're looking at to decide what things we're going to expire. Okay, so we've got this kind of everything's reorganized itself slightly. Then we're going to add another little blob in, and it comes in, takes first place, and everything shifts down in our cache. And let's add another blob. Okay, so now we need to pick which one we're going to expire. Well, we're going to expire the oldest one in the cache, this one. So what we're going to end up with is a gap in our table. So all the rows are laid out in these blocks in the table, but because we're not deleting them in the order we put them in, we might have some blocks where one row hangs around and another one gets deleted and so on. And what we get is fragmentation. So this is where you're not getting as efficient storage as you might. If you look at Memcached, it does some very clever stuff to avoid this. And databases do have things built in to help with fragmentation, but it's still a problem that we're going to see. Now, the thing is, that's not like the end of the world. We've already said that disk is cheap. So we can just probably, maybe our fragmentation rate will be like 20%. So, we just order 20% more disk. That's fine. But it's still an issue, fragmentation. We'll come back to that in a second again. The second challenge with least recently used is every time we read from our database, we're going to have to write because we need to update that access stat column. So every cache read is going to be select value where key equals whatever, and then update access stat equals time.now or whatever. So we've now got 2 operations instead of 1. So that's going to be a bit slower. Now, the things you could do, you could batch them up, do it in the background and so on. And that's how we first implemented this. But still, it's not ideal. So yes, so that was kind of what we were looking at there. So we were looking at least recently used, and we had these challenges. And then we kind of looked back at FIFO, and it's like, okay, well, with FIFO, we're not going to get that fragmentation, right? We're laying the rows down in blocks, and we're deleting the oldest ones first. We're deleting them block by block by block, and the database can just go and reuse them. You basically end up with like a circular buffer where you're going round and round and round, not fragmenting anything. So that's quite a nice feature. Second thing is that we don't need to do these writes when we read. We can just select from the table. It's just a single operation to read, and we don't have this kind of housekeeping to do to kind of keep updating things. The third one is we no longer need, like when we went back in that schema, we had an index on the created app field. We don't need that index because we can use the primary key index, right? The oldest items in our cache are the items with the lowest IDs. So we can just scan through the IDs. So, if you're talking hundreds of millions of rows, it's nice to not need an index that's on hundreds of millions of rows. The problem is, and the reason that people use least recently used and not FIFO, is you're going to get a lower hit rate for the same amount of data in your cache. That's like the point of least recently used. The point is you're keeping stuff that people ask for in the cache on the assumption that they're going to ask for it again. And that's a pretty good assumption to make. So our cache is not going to be as efficient. But we're using disk for it. We can make our cache 10 times bigger. On Basecamp, things stay in the cache for 2 months. So does it really matter if it's first in, first out? If you're going to get 2 months in the cache before you have to get out and back into it? We kind of went, we think that'll be all right. So it's worth it for the simplicity. And without the fragmentation, we can actually store more stuff in our cache anyway. So maybe that makes up for the hit of a slightly less efficient algorithm. Okay. The final kind of clincher for making solid cache into a FIFO cache was this one, our problem with estimating cache size. So we now have, hopefully, a simple proxy for cache size. So the thing, as we said, our data isn't going to be fragmented on disk because we're laying it down block by block, and we're kind of clearing those blocks up as we go because we're deleting the oldest items one by one. But the other thing is that our ID space is also not fragmented. So we're putting things in at the lowest IDs, and we're cleaning up those IDs as we go. So if you look at our ID space, that's just a window on our data that's going to just move along. So we can take the maximum ID and the minimum ID, add one just for accuracy, and that's more or less our number of entries. It's not actually going to be our number of entries because you might actually delete something if you call cache delete, or specifically in MySQL anyway, you get this kind of upsert behavior where if you do like an insert or update, it'll pre-allocate the ID, and then if it updates the record, it will just throw away the ID. So this is an upper bound. I mean, this equation is always an upper bound on your number of entries, but it's an upper bound that kind of matches the number of rows in the table. So that's the way we can work out what our cache size is. So we can use the number of rows as a proxy for our cache size. And this query is, we can do this in a single query. It's super, super quick. Getting the first and last ID in an index is very, very quick, and it's database agnostic. So that's what we went with for our cache size. And this is what our schema actually looks like. So we've got a key, a value, created at, and then an index on the key. And implicitly here, we've got the primary key and the index on the primary key. And the index on key is used for finding data, and the primary key index is used for deleting data. And this is what we saw when we plugged this in and the expiry process kicked in. So I was hoping it would work, but I didn't expect it to be like this, kind of just flatlining like this. But so we can see here, this is one of the databases we use to cache data on Hay, and it's just steadily climbing. And then at the point where this expiry algorithm kicks in, it just totally flatlined. One thing is the database never gives space back. So you wouldn't expect this ever to drop because the database is just going to hold on to stuff unless you start rewriting tables and stuff like that. But our aim was that it wouldn't go up, and in our case, it didn't. And it kind of relies on a certain homogeneity in your data, but that's kind of the bet we're making on that. Right, so talk through how we choose what data we're going to expire. The next thing is the actual process of expiring the data. What do we do? So as your application is running, you've got the cache there, and what we're doing is, per process, we're keeping a count of every time you write to the cache. And every 80 writes, we're going to start off an expiry task in the background to expire some data. So by default, this is just running on a background thread. That's kind of the plug-and-play aspect of this. You don't need any infrastructure for this. You can configure it to be an active job instead if you want, but that's not the default. Anyway, so this background job is going to run, and what it will do is it will find the 100 oldest records. And then it's going to look and see, is our cache full based on that check on the ID range that we've got? Or are these ones old enough, is our cache expiry 2 weeks, and these ones are older than 2 weeks? So it's going to take those two things and delete some or all of those records. Now, if you got the question, why is it 80 and 100? The reason for that is so that we can kind of apply backward pressure and shrink our cache. So if we only ever deleted 100 records for every 100 we wrote, we kind of would end up in this kind of steady state, or things could grow, but they could never really shrink. So say you've got your cache and it's set to, you say, I want the max age to be 1 month, and then you decide, no, let's make it 2 weeks. You need something there that's going to apply backward pressure and reduce the size of the cache. So that's the difference. These numbers are configurable as well. And just, yeah, it comes with sharding built in, just using the active record connection handling. So, the cache itself will take each key, apply a hashing algorithm, choose a database, and send it there and query from it there. Now, for us, and I think in most cases, you don't need to do this for performance. One database, in our case, would easily handle our whole cache, but it's really about resilience and sort of making things easier to maintain. You can swap these out and run in a slightly degraded mode, update the operating system, or whatever you want to do, or just swap in a new one without taking your whole cache down all at once. Okay, so that's kind of the features in there. So let's look at where we ended up. So this is how you would install it. So this was our aim, that it's plug and play. So you add the gem, run bundle, obviously, install your gem. The next step is to run a rake task that will install the migrations for that table. run db migrate, and add it in your environment. And that should be good to go. So that's the aim. In this case, this is the case where you're putting the cache into your primary database. If you want to, shard it or just put it in a separate one, you'll have a bit more work to do to set up your, set up the database in database.yaml and so on. If you want, you can add some configuration. There's some other options, but these are the main ones: age, the maximum entries, and if you're sharding, setting up some shards. Okay, so that's how it works. That's how we configure it. So I thought I'd talk just a little bit about how we use it at 37 signals. And yeah, let's go through that. So this is kind of super simplified version of our setup. So this is, well, Basecamp and Hay would roughly look the same, but we'll talk about Basecamp here. So we run it out of 2 data centers in an active setup. And in each of those at the moment, we're running with 4 MySQL 8 databases. That's specifically for our cache. So these are dedicated to the cache, and the key space is sharded across those databases. Right, so, and each database is using 20 gigabytes of memory and 3 terabytes of disk. So our entire cache per data center is about 12 terabytes, minus a little bit for some wiggle room, but so that's what we're looking at. So say 10 terabytes or so of space. And that's just sized based on, we wanted 2 months worth of data, and that's how much space we needed to be able to store that much data. Okay, if we look at how we're configuring those MySQL databases specifically, so we don't have replication set up on those. We're not doing backups, and we've kind of changed the default configuration so it's not fully configured for ACID guarantees. So it's not. We don't need that durability that every write we can guarantee is there. It's a cache. We can afford to lose a couple of seconds of data. We'll just regenerate it and put it back in the cache later. So specifically for MySQL, that's like we're f-syncing the data once per second rather than on every write. We're not using bin logs. There's like double write. We've disabled that. Every database, I think, probably will have their own version of these settings that you can do. And yeah, so the reason we've done this is for speed and simplicity. So the simplicity comes from there's no replication, there's no backups. So we don't need to worry about what's our replication topology, what's our failover strategy. We've just got a database, and maybe it'll crash. Data will still be on disk. Maybe the disk will get corrupted. We don't really mind. It's a cache. We can afford. We've got 4 of them. We can afford to lose one. We can replace it, and it just makes the infrastructure setting this all up much simpler for us. And as I said, our resilience comes from having those 4 databases rather than the individual resilience of each database. Said this before, 60 days of data. So we're looking at about 900 million is the max entry setting that we've got on each of those databases. Because of that behavior I talked about where you get gaps in the cache with upserts, I think it's more like there'll actually be about 600 million or so records in each of those 4 databases. So yeah, we're looking at, don't do maths in your head when you're talking, a lot of items. Right, so, and the last thing is our data is encrypted. So this was just 3 lines of code just to say, let's encrypt that value column in our cache. We can do that because we already have active record encryption set up, but if you do, it's super easy to encrypt that data as well. So it's encrypted at rest. Okay, so we've gone through that. So let's now look at how it performs for us. So here's the operation performance that we saw. So I went back and redid these numbers after David had done his slides, and they're actually both a little lower. So, so we've got, with Redis, a read. So just reading something out of the cache was 0.7 of a millisecond, and a write was 0.9. Now, these things are going to be highly, highly dependent on your infrastructure and how everything is set up, but these are just the numbers that we were seeing. And yeah, so with solid cache, we're at about 1 millisecond for a read and 1.4 for a write. I actually had to fudge these numbers a little because we were encrypting now, and for a fair comparison, I've kind of estimated what the encryption cost is, profiled it a bit, and took that out. So hopefully I've got it right. But we're sort of seeing a difference in the region of 50% slower. So our operations are slower, but these are small numbers, so they're still, they're still pretty fast. And like, if you look at what the difference is, like why is it slower? It's nearly all just slower operations. So, reads on our database is about 250 microseconds. So that's 0.025. And then there's a tiny little bit for kind of extra active record overhead, but kind of work to minimize that as well. Okay, so that's performance. So looking at whether it's cheaper. So these are looking at the storage costs. So what we're comparing here is our Redis setup that we had, what we had with RAM and disk on that. The storage costs are just based on list prices of the, the latest hardware that we've been buying, 37 signals. And so the big important bit is this RAM column. So before we had 1.1 terabyte of RAM for our Redis caches, and now we have 80 gigabytes for our solid cache. We probably didn't need 3 terabytes of disk before, but it doesn't really matter. That cost-wise, the disk, when you look at it, it's like 50 times cheaper than RAM. So it's, it's the 600 of that 4,600. So what we're seeing when we went through this is that our storage costs are, roughly a quarter of the size for the same number of gigabytes. And the number of entries we were able to store in each cache, you can see there. Slightly, you can get more things you can fit more data into like Redis and memcached per gigabyte than you can with the database, because the database has indexes and it does things like leaves space deliberately so it can fit new records in later and stuff like that. So, but when you do all the numbers, you're basically looking at the cost of the storage for 1 million items in our cache is about 20 times cheaper with solid cache than it was with Redis. So that was quite good. I've got a graph of our cache miss rate here. So this is over time. I've removed the time because they're time shifted. So the top orange line was what we were getting with Redis, and it was kind of steady state of 10%. These numbers are going to be highly, highly dependent on your application. But for us, the same application with the new cache, we were seeing it went down to about 7.5%. And it's more or less bottomed out around there. And I think like the sort of next step with kind of what to do with caching is the interesting part is like what's in that 7.5%. And if you look at it, it's just going to be stuff you've never asked for before. Once you kind of reach the point where your cache is virtually infinite, your misses are your initial requests. So if you want to look into, and I think that we've done a bit of work on Hay for this kind of thing, what you want to look at is, for getting those down, is can you predict things you're going to look at? Can you find behavior like this thing gets added? Well, let's just pre-render the fragment for it, and it will be there when we need it. So we'll probably look at that soon with Basecamp and see if we can get these numbers down a bit more. And then here's the performance graph. I think just a bit like the one David showed earlier. What's striking here, yes, it got a lot faster, but what was striking and a real surprise for me was how quick it was. Now, I think this graph is overselling the speed a little bit, partly because this drop happened over a weekend where we naturally have a drop anyway. And also, you can kind of see just before the drop, so the solid cache went live on the 1st, I think. But just before that drop, you can see this erratic behavior, and we spent a week introducing solid cache, so we'd kind of switched 10% of the keys over to solid cache from Redis. So you're replacing a full cache with an empty cache and so on. And that's kind of, so over that week, you've got this kind of erratic behavior, and there's kind of the droppings already happening, but you can't see it. But still, it was incredibly quick and a lot faster. Okay, so there was our conclusion. Would it be bigger, cheaper? We were kind of happy that those would be the case. And for us, was it faster? Yes, it was an awful lot faster. So one thing I'd say about that is Basecamp heavily uses fragment caching, right? It is an application that's set up to win from a bigger cache. And if your application is not set up to do that, you're probably not going to see the same benefits we did. However, maybe you'll just have the benefit of we can just move our cache into a primary database and get rid of a bunch of infrastructure. And that's, yeah, that's still a big benefit. And just about 10 seconds late, I think that's me. Done. So there's the repo. That's me. I don't really do social media, but if you're on the Slack app, you can find me on there, so send me a message and we can talk there. And that's it. Thank you very much.